Welcome to our quantum deep dive. Today, we're going to take a trip somewhere that sounds like it's straight out of science fiction, but it's totally real. I'm talking about the mirror world of antimatter.
Yeah, and we're not just, dipping a toe in the water here. We are going deep. We're going to try and understand one of its weirdest, most unusual inhabitants, this exotic particle called the Anti-Ξ-Baryon. And our guide for this whole thing is an absolutely fantastic essay by the physicist Jurgis O.A. Schneeppat.
Okay, so let's start with the big idea, the foundation for everything else. For every single particle of matter, the stuff that makes up, well, us and everything we can see, physics tells us there's a perfect mirror image twin, an antiparticle. And these antiparticles they're just fascinating. They're so similar, but at the same time completely different. They have the exact same mass as their matter buddies, but check out the proton and antiparticle here. Their electrical charge is perfectly flipped. And it's not just the charge. Other deep quantum properties like their spin are also inverted. It really is like a true mirror of reality, but on the most fundamental level you can imagine. All right, so to really wrap our heads around all this, we've broken down our journey into 5 main parts. We're going to look at where this whole idea of antimatter even came from. Then we'll get into the nitty-gritty of the anti-Ξ-Baryon itself. After that, how do scientists actually make the thing? Why does this little particle even matter? And finally, we'll look ahead to the kind of quantum future it might just unlock. So where did this wild idea of a shadow universe of antimatter even begin? Well, it wasn't discovered in some lab experiment or spotted with a telescope. Nope. It first showed up as kind of a ghost in an equation. Way back in 1928, you've got the brilliant physicist Paul Dirac, and he's trying to build a theory that mashes quantum mechanics and special relativity together to describe the electron.
But his equation, it had this little quirk. It spit out 2 solutions. One was for the good old negatively charged electron we all know and love. But the other for a particle with the exact same mass, but a positive charge. Now, at first, pretty much everyone, including Dirac, thought, nah, it's just a mathematical weirdo, a fluke. But Dirac, he actually took it seriously. He predicted the existence of an anti-electron. And get this, just 4 years later, a physicist named Carl Anderson is looking at cosmic rays, and he finds a particle track that looks exactly like an electron's, but it's curving the opposite way in his magnetic field. It was Dirac's anti-electron, which we now call the positron. The mirror world, it was real.
Okay, so that's the origin story, and you can see how that first mind-blowing discovery leads us right to what we're talking about today. I mean, we've come a long, long way from just simple anti-electrons. Now we're able to study these incredibly complex structures. And we're going to focus on something much heavier and way more exotic, the Anti-Ξ-Baryon.
Right, let's just take a second and break that name down because it actually tells you a whole lot. The word baryon, that comes from the Greek for heavy. It's basically the family name for particles like protons and neutrons. The ones built from 3 smaller things called quarks. So it kind of makes sense, right? An antibaryon is just made of 3 antiquarks. And the X part? That's what tells us it's a special kind of baryon. It's one that has something called a strange quark inside. And honestly, they were called strange because when physicists first found them, they just behaved, well, strangely. They stuck around for way longer than anyone expected before they decayed. So putting it all together, the anti-Ξ-Baryon is a heavy particle. It's made of 3 antiquarks, and at least one of those is an anti-strange antiquark.
This table really lays it all out, doesn't it? It makes those mirror properties super clear. So you've got the regular She0 baryon that's made of 1 up quark and 2 strange quarks. And then look at its antimatter twin, the anti-She0. It's built from 1 anti-up and 2 anti-strange antiquarks. A perfect flip. And just look at how those core quantum numbers totally invert. The baryon number, which is basically a way physicists keep score of matter, it flips from +1 to -1. And then strangeness, which you guessed it, keeps track of strange quarks, flips from -2 to +2. It's just a perfect symmetrical inversion.
So here's the really crucial point. While all those quantum numbers that give the particle its identity are flipped on their head, one thing stays almost perfectly identical: the mass. It's about 1,315 mega-electron volts, which is, roughly 1.4 times the mass of a proton. The key is the anti-C and its matter twin weigh the same. And that isn't just a fun fact, it's a cornerstone prediction of the standard model of particle physics. If scientists ever measured even the tiniest difference, my gosh, that would be a Nobel Prize-winning discovery that would completely shatter our understanding of the universe.
But, and this is a big but, this is where the challenge gets absolutely immense.
Just look at that number, 2.9 times 10 to the negative 10th seconds. That's less than a third of a billionth of a second. It's almost impossible to grasp. So to put it in perspective, in the entire lifetime of this particle, a beam of light, the fastest thing in the entire universe, can only travel about 9 centimeters, 3.5 inches. That's it.
I mean, the anti-Baryon just poof, it flickers into existence and vanishes almost instantly. So the question is, how on earth do you create something like that? And how in the world do you study it if it's gone that fast?
Well, the answer is you build machines that can recreate the most extreme conditions in the entire universe. You basically have to wind the clock all the way back to the very first moments after the Big Bang. If you want to find a particle this exotic, you have to forge it in an absolutely incredible fire. Yeah, you can't just find these particles lying around waiting to be discovered. You have to manufacture them. And you do it in these colossal particle accelerators, like the 27-kilometer-long Large Hadron Collider at CERN. Inside that ring, they take beams of heavy ions, think lead nuclei, and they accelerate them to 99.999999% of the speed of light, and then just smash them into each other.
And the sheer energy from that collision, it all comes down to Einstein's famous E equals mc squared, is just so immense that it melts protons and neutrons down into this primordial soup. It's a state of matter we haven't seen since the first microseconds after the Big Bang. They call it a quark gluon plasma, and it's this perfect liquid, trillions of degrees hot, where quarks and gluons are just roaming free.
As this fireball expands and cools, all that raw energy condenses back into matter, and that's when you get these exotic particle-antiparticle pairs popping into existence, including our Xi and the anti-Xi.
Now, you can't just snap a picture of the anti-Xi. No way. It's gone way too fast for that. So instead, physicists have to become something like subatomic forensic investigators. They have to sift through the messy debris of literally billions of collisions, and they're looking for a very, very specific set of footprints. Here's how it works. First, the collision creates the anti-Xi. It manages to travel just a few millimeters inside the detector, and then poof, it decays into other particles. But the story's not over. Those new particles are also unstable, so they decay almost immediately too. And this whole process creates this unique cascading signature, a really distinctive double V-shaped track in the detector sensors. So by painstakingly tracing these super faint footprints back to a single point of origin, scientists can prove beyond any shadow of a doubt that an anti-Baryon was right there. So think about that. We build these machines the size of a city, we have thousands of brilliant scientists working on them, all to create and detect a particle that vanishes in less than a blink of an eye. You gotta ask, why? Why go to all this trouble? Well, it's because this tiny, fleeting ghost of a particle holds clues to some of the absolute biggest, most profound questions in all of science. And this really is the ultimate mystery, isn't it? According to our best theories of the Big Bang, all that energy at the beginning of time should have condensed into perfectly equal amounts of matter and antimatter. A perfect balance.
But if that had happened, well, every particle would have quickly found its antiparticle twin, and they would have just annihilated each other in a massive flash of pure energy. Poof. The entire universe would be a vast, empty, sterile place, with nothing in it but light.
So the very fact that we are here, that galaxies and stars and planets and us could form, it means something broke that perfect symmetry. The theory goes that for every billion antimatter particles, there must have been 1,000,000,001 matter particles. That tiny, tiny little surplus, that's everything we see. But the question is, what caused it?
And this is exactly where the anti-Baryon becomes such a crucial tool. By precisely comparing its properties, its mass, its lifetime, the exact way it decays, to its matter twin, physicists are testing a really foundational symmetry of the universe. It's called CPT invariance. Now that's the bedrock idea that the laws of physics shouldn't change one bit if you do three things at once. Flip a particle's charge, that's the C, mirror its coordinates in space, or parity, the P, and reverse the arrow of time, the T.
What we're doing is we're searching for a crack in that fundamental mirror. Any tiny little difference, any deviation at all from that perfect CPT symmetry, could be the key. It could be the thing that explains the whole matter-antimatter imbalance. It could finally tell us why our universe survived. So really, by studying these particles, we are opening a direct window into the physics of the Big Bang itself.
Okay, so we've seen why this particle is so important for understanding our cosmic past. But you know what? The story doesn't stop there. Looking forward on the quantum frontier, studying the properties of exotic antimatter like this could seriously reshape our technological future. Right now, this is all purely fundamental research. It's driven by a deep curiosity to just understand how things work. But if you look at history, it's always the knowledge from the cutting edge of science that ends up seeding the technology of tomorrow, often in ways that nobody could have predicted. And theorists? They're already playing with some pretty visionary concepts. Take quantum computing, for instance. Right now, information is usually stored in qubits, which can be a 0, a 1, or kind of both at the same time. But the really complex internal quantum states of a heavy particle like an anti-Ξ-Baryon, well, theoretically, you could use that as a multi-state qubit. It could hold way more information, a 0, a 1, a 2, a 3, and so on. That could potentially unlock some immense new computational power. Or maybe, just maybe, its unique properties could be used to build incredibly sensitive new quantum sensors. And of course, we have to talk about energy. I mean, the whole idea of antimatter power is a staple of science fiction for a very, very good reason. The energy you get from matter-antimatter annihilation is just mind-bogglingly efficient. It is the most potent energy source the laws of physics will allow. That 90 terajoules from just a single milligram, that's more energy than was released by the first atomic bomb. Okay, but let's be totally clear here. We are nowhere near doing this. The sheer difficulty and the just astronomical energy cost of producing and storing even a few antiparticles makes this pure speculation, at least for the foreseeable future. But what it does do is powerfully highlight the immense potential that's locked away inside the physical laws that this kind of research is helping us understand. And that kind of brings us to the final thought we want to leave you with. We've taken this journey into a mirror world that is almost, but maybe not perfectly, identical to our own. And we now believe that that tiny, mysterious imperfection is the only reason that we and our entire universe even exist. And it just forces you to wonder, doesn't it? What other subtle cracks in that mirror are still out there, just waiting to be found? What other fundamental truths about the very nature of reality are hiding in plain sight, waiting for the right experiment, or maybe the right particle, to finally reveal them? So, the Anti-Ξ-Baryon, it's this fleeting ghost from the dawn of time, forged in the heart of a massive collider. It's a tiny, tiny particle that forces us to ask the biggest questions imaginable. It really makes you confront the nature of reality itself and the profound, beautiful mystery of why we're here at all.
We really hope you enjoyed this deep dive with us, and our sincere thanks go out again to physicist Jörg Owe Schneepatt. His insightful essay was the perfect guide for our journey today.
If you want to read the original work and explore this stuff even further, you can visit schneepatt.de.
Goodbye.
Schneepatt.de is a private project by Jörg Owe Schneepatt dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.